Hi. So right now you're probably wondering, how do you convert alternating current into direct current? I mean, this is a very important question. Like, for instance, this right here is a phone charging adapter. It takes alternating current from the wall and converts it into direct current because alternating current can't charge your phone, but direct current can. So, how does it do that? Also, you might be wondering, why are you showing your face? And the answer is because I'm bored. Roll intro. So at first, before we start, a good thing to explain is what is the difference between AC and DC in the first place. But before I do that, I have to put on my secret hat. So DC, or direct current, is when the current always flows in the same direction. So it just goes whoop. But AC, or alternating current, is when the current shifts direction back and forth, like pew, 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 pew. And another important thing to consider is that in alternating current, the current always switches back and forth, but the voltage always switches back and forth. And then in direct current, the voltage is always constant. Okay, I can take off my hat now. And we can actually measure that changing voltage with something like this, an oscilloscope. So I plugged in the scope. So what we can do to measure the voltage now is this thing right here. You can use that to measure voltage. So we can put this on the end like that, and then leave it there, and then plug it. Dang it. We have that on there, and now we can plug this into there. See that? It's measuring the voltage from this slot right here. This is what's known as the hot slot right here. And then this right here is the neutral slot. See, so there's no voltage, but it's the hot slot. And there's voltage. Well, how much voltage? Well, you can tell by looking at this cyclic RMS value, and it's about 124 volts right now, which makes sense because in North America, we have 120 volt RMS. And what's the frequency? Well, frequency is up here, and it's about 60 hertz, which again makes sense because the frequency of electricity in North America goes back and forth 60 times a second. So, the more you know. Alright, so before we move on, I have an important safety consideration here. So as you can see, it's plugged in and probing the voltage, and there's a better view of the voltage right now. It's 122 volts RMS. But that right there is exposed live voltage, and I can prove it to you by... Hold on, wait a minute. I'm gonna have to put you in darkness for a little bit. Okay, here we are. And if you touch that to there, it turns it on. Pretty. Oh, damn. Okay. So, what does a DC source look like with our scope? Well, it's pretty simple. Just attach the ground to there, and then attach the probe to right there. Okay, you can't notice much. Hold on. If I turn the voltage registration down, and see that? It moves up a bit when I complete the circuit. Again, this is a total of 3 volts DC, so again, not much, but I believe that through the power of science and technology, we can convert alternating current into direct current. So before I can show you how to convert alternating current into direct current, first I have to create a source of alternating current. Now I could use the wall, but that would probably blow these components up. But using this circuit, I can convert the 3 volts from these two batteries into short pulse alternating current. So what happens when you press the switch is that current flows through the T1, which is the transformer, and so a very high voltage pulse is created on the output of this transformer, and you can see that whenever I press the switch on the scope. See, look at that. Look at that peak to peak. You've got almost 500 volts. But again, it's very brief. Look at that. It's taking a sample every 40 microseconds, or at least that's what the screen is showing. Span of 40 microseconds. So, but this will be good enough for me to demonstrate how the converter works. So for me to be able to convert the alternating current on the output of the transformer to direct current, I need the square of awesomeness. This specific square of awesomeness is known as a full bridge rectifier, and it's composed of 4 diodes, 2 of which let current pass through that way, and 2 of which that let current pass through that way. But these are very special kind of diodes known as light emitting diodes. So this means that we'll actually be able to see when current passes through each one because they'll light up. So now I have the circuit arranged like this, and if that's confusing, that's fine, I'll explain it to you. So right now we have the output of the transformer going to here and here, and this right here is a current meter, and it's kind of a high resistance current meter, or just higher than it should be. So then we'll be able to probe across the ends of the current meter and then be able to measure them on the voltmeter. So from here, from these 2 points where the current meter is, this is where the direct current should go. And you'll also be able to see the full bridge rectifier diodes light up. So see, check that out. So what's going on is that each time I press and let go, different currents flow through each of the different diodes. But look at that. Each time the current is always going in the same direction, and you'll be able to see it on the hold up. You can't really see it well, so I'll have to change that to better. Okay. There we go. So if I keep pressing them quickly, look at that. The current, or the voltage even, is going in the same direction each time. Now the voltage isn't as high as it was before because again the circuit is complete. But look at that. Isn't that so cool? But one thing that we can do is, instead of getting a short pulse of DC, is we can get long period of DC. And so we'll see how you do that now. Now what I did is I connected a 470 microfarad capacitor in parallel with the current meter and also the probe. So let's see what happens now. Now watch the current meter. Look at how long it took to go back down to 0. That's because the capacitor holds voltage, so it's actually holding the voltage constant for longer, and it makes our voltage, or current in this case, look more DC, but makes it look more DC looking on the voltage side too. Look at that. Look at that. It's holding it flat right there. So much so that this thing can't even figure out the frequency of it, right? And again, we're actually probing along a time period of 25 times longer than we were before at 800 microseconds. Now it's 20 milliseconds. And it looks pretty DC looking. Now again, the voltage is much lower, but still. Our goal is to get DC, and we've basically got it. But we can still do better. So this whole time I've been using a press switch where the fastest I can go is like that fast, but I can just get rid of that and use something that I can go much faster with, the vibration switch. Now I'm going to switch back to the forward view so that you can get a better sense of what's going on, because shaking this vibration switch while holding the phone is going to be hard. So just watch what happens now. Look at that, the voltage rises much higher now, and it looks almost flatter. Now if I could shake this at a constant rate, it would look very flat, because the higher the frequency that the AC goes at, the better the job that the capacitor can do in filtering it. Like for instance, look at how fast the lights flicker back and forth now. Look at that. Again, we're using the same time scale as that, but look, got a much higher voltage now. So right now you're probably wondering, is that pretty much the same circuit that's used inside of here? And the answer is, yeah, yes it is. Now this has another component that I don't have, so I can't really show it to you, but this has a regulator inside of it, and what the regulator does is it limits the voltage at 5 volts, because you saw that on the peaks it could sometimes like get kind of high, so this limits that, so it makes it look even more DC looking, so that's pretty much just a flat line. So yeah. So to review, the alternating current travels through this full bridge rectifier, which forces the current to always travel in the same direction. Next, a capacitor is placed in parallel with the load so that it holds the voltage steady. And finally, a regulator, which isn't here, makes sure that there aren't any voltage spikes. And voila, direct current.
That was easy.
If you have any feedback for this video, please leave your thoughts down in the comments. Also, if you have any ideas or topics for future videos, again, please leave your thoughts down in the comment. Thank you and have a nice day.